Here's where we can see it. The torque itself, this is the symbol for torque. It's the symbol tau. T-A-U is the way it's spelled, but the symbol is tau. Torque equals R-F sine theta. Ignore the sine theta just for a minute. R, in this case, stands for distance, right here. Distance. F stands for force. So in yesterday's lab, you guys actually derived this. You wrote down that it was the Hooke number, which was distance, and the force applied, which was the mass you wrote down. So whether or not you necessarily see that this is as simple as what we saw a minute ago, recognize that it's the same thing still. It's analogous in nature to what we wrote down yesterday. Now, R is specifically defined as the length between the actual rotating axis and where the force is applied. The rotating axis and where it is applied. Steve.
How is that differentiated from that?
Steve, I'm so glad you asked that, because the other class, no one asked that, and I was waiting for it. How does that change from work? I went into this with them because no one asked it. It's the same formula, right? What was the formula for work? Work equals FD cos theta. It's pretty much the exact same formula, Steve. You're totally right. You're totally right, actually. Here's the difference, Steve. This, because numerically it's the same, right? A force times the distance. A force times the distance. Cos theta, sine theta. Pretty much the same thing, right? Unit-wise, this is measured in newtons times meters, and my units of this are newton times meters. But with work, what did we call the unit? Joules. Because that had to do with distance that's translational and the object is moving. This distance in work, remember, was how far it actually traveled. It's a different distance than the R itself here in the formula, which is the distance not traveled, but the distance between the rotating axis and the applied force. In work problems, did anything rotate now? Nothing to do with rotational. It was linear. Move left to right, move up and down. So yes, the equations are very, very similar. And although the units of this were Newton times meter, which is a joule, Newton times meter is definitely a joule, we do not call these joules to differentiate between something that is linear motion and rotation. Yeah? Great question. Great question. Now, I was waiting in the class and I actually pointed it out. I think Rodrigo eventually asked, but I have to prompt, Say, oh, come on, you've seen this before, and then figure it out. Now, theta in this problem is a very specific thing. Theta is the angle between the applied force and the direction of the lever arm. Okay? In this case, I think I called it the direction of the distance R. I haven't used the phrase lever arm yet. We'll do that in the next slide. Okay? So, theta, where theta is the angle between the force applied and a line drawn along the direction of the distance. So right here, take a look. This is the distance line right here, and this is the force applied. So this is theta right here. Okay? If I think about the diving board, as I walk on the diving board, I'm taking steps. That diagram would look like this. Oops. This is the diving board here. And as you step, that would be your applied force on a diving board, as you're literally stepping forward. And then you would push off and push back, so then that force would look like this. But it doesn't matter which angle it is. All that matters is that you know it's rotating here. This is the distance away. This is the force. So there's your theta. So look, here theta is acute. Here, theta is obtuse. Doesn't matter. It could be either one. Okay? Theta could be any angle between 0 and 180. Okay? Theta is any angle between 0 and 180. We're going to get into a little bit more of that with the sine function in a second. Okay, but just recognize that theta can be any angle between 0 and 180. And if you think about it logically, if the angle were 180, what would happen? Imagine a 180 degree angle for the force, right? So watch. Imagine the angle is like this, which would mean the force would be applied. The force itself would be applied like this. Right? That's an angle of 180. There's the actual distance line right there, the force. There's the force itself. There's the angle between. What happened with this object? What?
You're saying what it would be?
Like, so if there's a pin here, right? Imagine this is not a value board anymore. And there's a pin there, and I want this thing to rotate. I don't want to give it away, so I don't want to give any more questions. But what would happen here? It would really just be a push, right? Would it rotate at all? It wouldn't. Use logic, right? If I wanted to close this door. To close this door, I push like that, right? Which causes it to rotate. But what if I push like this? Is it rotated? This is the lever arm here, bar. This is the force applied. When the angle is 180, and I push on it at an angle of 180, it's not going to rotate. I need to have a little angle, right, to cause it to rotate. Go in your calculator real quick. Type in the sine of 180. Type in the sine function here of 180. It's not -1, that was cosine of 180. That was from the word kinetic force here, that being cos theta. Right? Cos 180 is -1. It's 0. It's keep looking out, so I have to do more of this, so keep the calculators out. So when you apply a force at an angle of 180, it's not causing any rotation at all. And that's logical. Well, take a look. R times F times 0 gives you 0. If you have no torque, it's not going to rotate. No torque means no rotation. And again, you're not sure about what I'm saying right now. Think about if I took this wrench here and I wanted to just bend the metal back. I'm not going to do it because it's going to deform, right? But if I wanted to take this little ledge here and bend it down, when I push down on the wrench, I push down like that. But if I push like this, is anything happening? No, because I'm pushing into this. It's like me pushing here. Nothing's happening. It's not causing it to rotate. And that's the 180-degree angle. Sine of 0 degrees is also 0, by the way. So if I apply force in this direction, instead of the force being pushed in, let's say I pull outward. Okay, let's do it one more time. Here's the door. I take the door and I pull outward, and I pull and I pull. Is it moving? No. Because I'm pulling this way, the R value is this way, which makes the angle now 0 degrees. If I continue this dashed line, and I think about this force, the angle between this and this is 0. Sine of 0 and sine of 180 are both 0. So the idea is that when you want to create torque, you need to apply a force at an angle. Okay? At an angle. Not an angle of 0 or 180. Alright, let's go on to the next slide. I'm going to see if there's anything else. Oh, actually, sorry. One more thing. I knew it. We talked about vectors before a couple times. And torque is also a vector. Other examples of vectors we've talked about are displacement, velocity, forces, and now torque. Displacement, velocity, forces. Why are they vectors? Forget torque for a minute. Displacement, velocity, and forces in general are vectors because of what reason? What is the definition? Because I'm going to remember. I didn't give you the hint. I said think about the definition of a vector. What is a vector really? It has a magnitude and a direction. Very good. So when I apply a force this way, it's a positive force. A force this way is a negative force. This is negative displacement. This is positive displacement. So we have looked at linear vectors. Agreed? This is going to be a rotational vector. So which ways can this rotate? What are the two ways you can rotate? Two ways. What do we call them? How can something rotate?
Clockwise, counterclockwise.
Good. Clockwise and counterclockwise. Now, some books will call that anti-clockwise instead of counter. Same. I know. It's an old phrase. Same thing, though. We're used to counterclockwise. Here's the traditional acceptance of this. Ready? If an object is rotating with the clock, clockwise, versus counterclockwise, okay? Clockwise is considered negative torque. Counterclockwise is considered positive torque. It's an adoption that physicists made eons ago. I don't know, actually, not long ago, but a long time ago, that has been used since I've started studying physics. It's always in every book the same way. Clockwise is negative, counterclockwise is positive. I personally think it's a bit counterintuitive, because when I hear the word counter, I think of negative, so I'm like, oh, that doesn't make sense. But Adrian O'Sullivan came up with a way to remember it, and it's very simple. I asked, anybody come up with a mnemonic device? Mnemonics are things that help you memorize, right? his mnemonic was this, and we sat for like a minute. One letter C here, right? And one little dash. Two letter C's, and two slashes. I know it's not really, it doesn't mathematically hold true, but he said, you know what? Clockwise there's one letter C and we have one little line. Counterclockwise there's two letter C's and in the plus side we have two lines. That's how he remembered which was. It works. And if this helps you, use it. But you have to memorize this. It's rare that I tell you to memorize stuff, right? But you know you memorize left and right, so now we have to start memorizing clockwise and counterclockwise. Okay, so if you're going with the clock, it's negative. It's negative. How do I know if I'm going with the clock or not? For example, this one here. If there were no other forces acting on this member and it were fixed at the pin, this is a pin, so imagine here's the pin, it were fixed here and I push down, which way will this rotate? I push down on this side, which way will it rotate? We got it, listen. How come? Yeah, we see it, this gets pushed down and loops around. That's the direction of the clock, right? I'm doing it from your perspective, not mine. So this is clockwise for you guys. You're seeing it literally move with the clock, and this will move freely. So with these problems, we are going to really focus on several forces applied on one member and try to find out if it's actually rotating, if it does, which is stronger. Is the force this way causing more rotation that way? Or is the force on this side causing more rotation that way? If they're balanced, what are we in the state of? Equilibrium. In this case, it's rotational equilibrium as opposed to force equilibrium. Later in the year, we'll talk about thermal equilibrium. But the phrase equilibrium should be pretty common sense to you guys by now because I've used it a lot. Okay? Good for the adoptions of signs. We need to know those values. All right. Now, this is a slide that honestly, I think every year does have a tendency to confuse people. So I'm going to go a little bit slow here. And I'm going to try to go as slow as I can. Not taking too much time. Now, I like math, you guys know that, and it's very easy to prove what I'm going to tell you mathematically. I'm going to first try to show you it logically, okay? So for anyone that's ever used a wrench before, and I'll use the cheater bar for now so you can see it better, okay? If you've ever used a wrench before, let's say I take the wrench and put it on the end of a bolt. You would use a bolt, then you would use a wrench to loosen a bolt or a nut. And usually you have two wrenches, one that holds the head of the bolt still and one that can loosen the nut, or vice versa, but they have to be held still. So let's say I have the bolt here and I'm trying just to loosen that bolt, right? So the end of the wrench goes around it. I can apply a force straight down. I can apply a force at an angle. I can apply a force like this at an angle. If I apply a force this way, we saw nothing happens, right? So the idea I want you to see is that if I apply a force at a 90-degree angle, I'm going to get the most torque at it. And the reasoning, take a look at the little red lines, the dashed red line. The red line is getting smaller as theta gets smaller. This diagram is read this way. Read it from here, starting, put a little number 1 maybe. Stage 1, stage 2, stage 3, stage 4. Might help for later when you study. So when I apply a force at 90 degrees, I'm getting the most torque possible. But the minute I start to decrease this angle, my torque is going down every time. I'm getting a shorter, what's called lever arm. This phrase, lever arm, is the perpendicular distance from where you're rotating to the line drawn in the direction of the force. Let me explain that a little bit better with the diagram. I'll use a separate diagram for this. So, for example, can I slide this over enough? Okay. So if I had, here's the rotation point. It's always going to be a dot. Okay, and I'm going to use rectangles for the members themselves. So there's the member itself, and it's going to rotate around that pin. So if I were to apply a force straight down, and I want to figure out what the lever arm is, here's what I do. I take the force and physically, mentally, this is from your math class, translate it, slide it over until it's on the dot and parallel to the way it started. So stay with me, okay? I'm going to take a line that's identical to this line. I don't know if I can actually grab and move these. Hopefully I can. And I'm going to, come on, tell me I can do this. No, of course I can. I hate this app sometimes. So I'm going to take that line and just slide it over to here is what I'm saying. The distance between those lines is called the lever arm. Now, you might be saying, who the hell cares, right? because that's just the distance that we've been defining all along. Well, when it's 90 degrees, this distance right here is the same thing as r. The lever arm is r when the theta is 90 degrees. So this, if you recall, this is defined as r originally, while r and the lever arm are the same in the first circumstance because I'm pushing at 90 degrees. I'm going to show you the second one a little bit better than the way they're showing it. So now we have the same member. Okay. We still know that the force is applied at a certain distance r. So the same r value, nothing's changed there. But now we're going to go ahead and apply a force at an angle. At an angle. Watch what happens. So I'm going to use the same color again. I'm going to apply a force like this. Okay? What I need to do, again, to determine the lever arm, it's a phrase that's useful in physics, is take this force and slide it until it lines up with the dot again. But it needs to stay parallel to where it was. Again, take the force, and you're allowed to do this. It's an engineering thing I learned. You slide it over, literally, until it coincides with the point of rotation. So let's draw a dashed line over there now. I need it to be parallel. So that's the dashed line I'm referring to. So earlier I put a solid red line. We could have made this a dashed line or maybe a blue line earlier. Let's use blue to show this line that we're sliding. Now, the distance between this blue dashed line and the applied force is called the lever arm. If you look at it, it says the perpendicular distance. This, if I put a line between them, has perpendicularity in both cases. So the lever arm, in this circumstance, I'll use green or yellow I'll use. The lever arm is the distance between these two parallel lines. And it's got to be at a right angle always. So it's not obvious right away, but what you can recognize here is that the yellow lever arm is less than the r value now. In the beginning, when I'm at 90 degrees, the lever arm and the r are the same thing. So pause, because it seems to be a little confusing. Type in sine of 90 degrees in your calculator. Sine, don't call it out, just type it in for a sec. Sine of 90 degrees. Okay? Now call it. What do we get? What's the answer? 1, right? So when I'm at a 90 degree angle, take a look at where I'm pointing, please. When I'm at a 90 degree angle, this value here becomes 1. So the lever arm, by definition, is this whole thing. But when I'm at 90 degrees, this becomes 1, which leaves me just with r. A 1 times r is simply r. So in the first scenario, the lever arm, which can be calculated using this right here, the lever arm is the same as r. But the minute I'm at some angle theta, okay, recalling that this is the angle theta right here. There's theta, okay? The minute I'm applying a force at an angle theta, I'll call that angle 60 degrees. Okay, 60 degrees. Type in the sine of 60 degrees. 0.866 should come up, right? Good. It's a number you will memorize this year. I didn't just know that. You'll memorize it in your math class. It's the square root of 3 divided by 2. So it's called a reference angle. Your reference angles will be very useful. You're going to do it later in the year, so just wait till you get there. But the sine of 60, what I want to point out, is not 1, right? It's a decimal value less than 1, 0.866. And that idea is that the lever arm becomes less than what it actually is when it's not at 90 degrees. So this becomes 0.866 times r when I use this setup. But when I use this setup, it becomes 1 times r. Well, what's bigger, 1r or 0.866r? Well, clearly 1r, right? The number 1 is bigger than 0.866. So when I apply a force at a 90 degree angle, I get the most torque out possible. When I apply a force at an angle less than 90, I get less torque. How much less? It depends on the angle. So let's write a statement. As theta increases from 0 degrees to 90 degrees, the torque increases. In words, it says, as theta increases from 0 to 90 degrees, the torque itself increases. And if you want to try on your calculator, you can. Start with 10. Do sine 10. Do sine 20, sine 30, sine 40, sine 50. Keep trying. And what you're going to notice is that your answers keep getting bigger and bigger and bigger and bigger and bigger. The sine function you're going to learn this year is a function that increases strictly from 0 to 90 degrees. After 90 degrees, it actually starts to decrease again, and we'll see more of that in a little bit. But I want you to recognize this. This is the key here, from 0 to 90. 90 is the most, and we said a minute ago, if I apply torque, if I want to rotate a bolt, right, like this, and I apply torque at 0 degrees, is it rotating at all? Because what's the sine of 0? It's 0. So this makes the sine function 0 up there, r sine theta, that makes it 0. This makes sine of theta 1, and we can see that anything between is between 0 and 1. What do we got for a bell in this period, so I don't want 8 minutes? Thank you, Alex. Let's see. Now, if you recall from the last slide, we defined torque as R, F, sine theta. I could also write torque like this. F times R sine theta. And I'm allowed to do this. I can introduce parentheses because of the associative law of multiplication. I can change the order because of the commutative law. So I'm allowed to write it that way. And then if I look at the problem, I can see that really torque is a product of the force applied and the lever arm. Torque, tau, equals the force applied times what we're calling the lever arm. Lever arm. So if you have a bigger lever arm, the cheater bar, you have more torque. Okay, now, mathematically speaking, you're not going to have to worry too much about this diagram and stuff. You're going to be able to use the formula strictly. But I want you to be able to visualize what's happening here is what I'm showing you now. But we're going to see in a couple minutes or a minute or two that the math we're going to do, we don't have to worry too much about finding out what the lever arm actually is and stuff. We're going to be able to apply the first formula at the top. Okay, but the idea of leverage should make sense to you because if I'm pushing on a wrench upward and its angle is like this and I push up, you're not going to get much leverage at all. But if the wrench is like this and I push up, I'm going to get a lot of leverage. And for anyone that's ever used something like this, when you use a wrench, you literally, look at my arm. What's the angle between my arm and the actual lever? 90 degrees, right? See that angle right there? And as I rotate, and if you've used a wrench, you'll know that when you rotate a wrench, you actually rotate your arm also. And obviously, eventually, when it gets loose enough, you can sit there and spin, or you can use what's called a socket wrench or something, right? Socket set. It's a little easier. So it's a whole other thing. Okay, so that's what torque is, the idea. It's a force applied at a given distance from the rotating axis. So let's look at an example, I think. Yeah, perfect time. An example of this. Take a look at this one on your own, read it, think about it. Maybe suppose an answer to it if you can. Chris, what do you think?
I think
your head, you look like you got it right away.
I think you got the same amount.
Why, Chris?
Because I think it kind of works like when you're just doing in the lab. Like there's 1 meters and 2 meters, and the force is double.
So what he's recognizing is, look, isn't this force double this force? But isn't this distance away double this distance? And what did we just say torque is a function of? Torque equals, again, R times F times sine theta. Well, theta's not given. So Chris, what did you assume theta was in this case? Based on the diagram alone.
0.
Here's the R. Here's the force.
180.
90. One of the three ones, right? You have the right idea of this thing. So the force is applied downward. The distance from the rotating axis is horizontal. Horizontal and vertical makes a 90-degree angle right here. So what is the sine of 90 again? 1. So when problems are applied at 90 degrees, the formula simplifies to this. When torque is applied at a 90-degree angle, it's RF. In calculus and stuff later, you're going to learn R cross F. It's called a cross product, and you could have torque in several dimensions, in the X, and the Y, and the Z, and the same formula applies, except this becomes what looks like a time symbol when we've learned. It's called a cross product. So the torque applied at 90 degrees is what we're looking at here. And again, what do we have? 20 is the force, times 1 is the distance. Remember, r is the distance. 20 times 1 is 20 for this guy. Great. Next one. 10 is the force going here. But the distance now is 2. 10 times 2 also gives me 20. So in both scenarios, the applied torque is 20 Newton meters. 20 Newton meters. Okay? I'm going to probably stop there. There's another problem we'll start with tomorrow. Okay, tonight there's no homework in this section. You can start the homework if you want. You're welcome to. Okay, to give you an idea of what we're going to be working with tomorrow and on your homework problem, it's going to be stuff like this, where there's multiple forces. And the question is going to be, is it going to rotate? Is it in rotational equilibrium? Or is one torque more than the other so that it does rotate, and if so, which way? And you can calculate the torque from this guy alone, find the torque from this guy alone, and then remember that symbol? Find the sum of the torques. Just like we did the sum of the forces. If this force is more than this force, which way is it going to move? It's going to move this way, right? If the one arm is stronger than the other. If one torque is more than the other, it will rotate now, instead of sliding left to right. We're going to go into this tomorrow. Now, I'm going to pause at this point and go into the project. Questions so far on this stuff before we go on? On Moodle, go to Documents and Handouts. Quarter 3 project, please load. And we're going to find the sum of all the torques acting, just like we did with forces. With forces, we did the sum of the forces, and we set it equal to MA sometimes. We're going to just, for now, we're not going to set it equal to anything. We're just going to say, let's find the sum of the torques, which is torque 1 plus torque 2. However many forces there are that many torques. That many torques. Could be a zero torque from what event if it's applied at a 0 degree angle, like we showed. So if I wanted to add these together, I have to recognize, think about my pivot point. Here's my pen. Hold your pen where the pivot point is. Take your finger, push down or up on your pen in the direction of the force. So this force is pushing down, so watch what I do. I push down on the end, and what do I notice? Which way does it turn? When I push down, which way does it turn? Clockwise. And clockwise was negative torque. So F2 will cause a negative torque. F2 will cause a negative torque. What do you think F1 will cause then? Positive torque. They're both pushing down, but one is on the other side. So when I push down on the left side, I get a counterclockwise rotation, which is really positive torque. So as a result, when I'm adding these values together, yeah, torque 1 will be positive, but torque 2 actually we're going to use a negative sign instead of a plus. So generally speaking, we write it this way to start, and then we go ahead and plug in our numbers with signs. So we could put equals, and the formula is F times R times sine of theta. And here now I'm going to put a minus because now I know which way it's turning it. F times R times sine of its theta. But I know these values are all given in the diagram. F1, R1, those are both given right away. From the diagram, the force acting on the left side is 20 newtons. The distance from the actual pivot is 4 meters. The angle is 90 degrees. The sine of 90 degrees is 1. So I don't have to put that really. Okay, again, if you want to write yourself a note, this becomes 90 degrees. And the sine of 90 becomes 1. Remember what I did? I talked about putting this going to 1 instead of going to 0 like we've done in the past. All right, question becomes, I know F2, I know R2, but what is theta 2? What is theta 2? And we talked lightly or quickly about this in class 2 days ago. Quickly talked about it. What is theta? I'm not going to use 30 degrees is what I'm saying. Sarah's saying no. I agree with Sarah. Sarah, why are you shaking your head no? Why not 30 degrees? Okay, good. Sarah realized that this is the side you need to use, which is 150, and she's right. The definition of theta in terms of torques has to do with the angle between the actual R and the force applied. The R value is right here. The force is right here. So what's the angle? The angle is 150. Now it turns out Not coincidentally, but it turns out that the sine of 150 is the same thing as the sine of 30. So had you used sine of 30 by accident, you would actually be okay. But that's one of those circumstances because the sine function has a what's called supplementary angle function to it. Like if I had 170 degrees, it's the same as the sine of 10. Sine of 160 is the same as the sine of 20. Whenever they add up to 180, those sine values are actually the same, it turns out. And that just happens to be something about the sine function. But it doesn't work for the cosine of the tangent function, so don't just make that assumption, right? That we can just use the supplementary angle out of nowhere. You will learn what functions have different techniques and tricks to them in your math class so that you can definitely apply it in physics, and especially if you consider AP Physics next year. A lot more heavy math and trig in AP Physics. So 15 times the distance times the sine of 150. What do I get for an answer? What do I get for an answer? Give me a number. Thank you. 57 and a half. And my units are Newton meters. Okay, those are the units for torque. Newton meters. Newton meters. Who are we missing today, guys? One person. Marco. That's who it is. Okay. All right. So does it rotate? Does it rotate? What's the answer? How come? How come it rotates? It definitely rotates. Why? What would the answer be if it didn't rotate? If it weren't going to rotate as a result of these torques, what would the answer be? Yeah, so what would your answer be then? In a state of equilibrium, what would you get as an answer? When everything is balanced, what does your answer become? Zero. Remember with forces, when are you in a state of force equilibrium? When this force equals this force, and now you're balanced, right? If this force is greater, it's going to push. So that's what's happening here. If this comes out to be zero, it means that this positive torque was counteracted by the negative torque, and then it would be balanced. But this says positive. Positive means counterclockwise. So therefore, as Steve supposed in the very beginning, it will be a greater torque from this guy. And we can see that because this turns out to be 80, and this is, what is this? 12, 20, 22.5? 80 minus 22.5. The 22.5 is not enough to combat the 80, leaving behind 57.5 Newton meters of torque in the counterclockwise direction. And again, why? Because my answer is positive. What if my answer were negative? Which way does that mean it's turning? Clockwise. Again, we'll write it down. Maybe that helps you to pick up on that. Because my answer was positive, this rotates counterclockwise. If the answer had been negative, it would have rotated clockwise. If the answer had been zero, as Noel said, it would be in rotational equilibrium. It would not be rotating. Questions? I'm going to go a little bit quick. Not rushing through it, but I'm going to continue because I think we really understood this from last class. Take a look at this one. Spend like 30 seconds reading through it. Identify what's different about this problem than the last problem. Okay? Spend about 30 seconds, read through it. So from the first sentence alone, what are we trying to do? From the first sentence alone, what are we trying to do? Yeah, very good. So let's figure out this value right here in the diagram. That's the goal. It says, where should the 10 Newton force be placed, right? And that's R. So we're looking for R. Very good. In order to be in a state of rotational equilibrium. From the last problem, what does that mean the sum of the torque should equal? It's a rotational equilibrium. Zero. So we know already that this plus this equals zero. That's my governing equation this time. Whereas in the last problem, you were not told it was in equilibrium. You were told or asked, what is the overall torque? Now, we're not asking for the overall torque because we don't have this distance, so we can't find the overall torque. Instead, we're told equilibrium, which means the overall torque, as Alex said, is indeed zero. Because of the fact that we have equilibrium, we can sum them and set that sum equal to zero. Now, some will be positive torque, some will be negatives. We've got to figure that out from the diagram, right? So there's a good amount of stuff we have to actually label and figure out. So how do I know whether it's positive or negative torque? Again, I take my pencil, I put my finger where the pivot point is, I take my other hand, and I apply force. So let's take a look at the 15 Newton force first. As I push, what kind of torque does that give? Negative torque, very good, because it's clockwise. This one becomes what kind of torque? Positive torque, because when I push down on the left side, it's going to make it turn counterclockwise. And then I go over to here, and I push down on this side. What kind of torque is that? Again, negative, because it's clockwise. I heard negative from the few. We should know that quicker, right? So let's just think about it. This one, right here, 15 Newton, would cause it to rotate like that, right? That's the rotation that it would cause. So we say again that that's clockwise. So that's going to be a negative torque. This guy that's 25 newtons right here will cause it to rotate like this, right, in that direction, which is counterclockwise. So that would be a positive torque. And then finally this last force over here that's 10 will cause it to rotate like this, which is clockwise. Clockwise again is negative torque. So one of these provides positive torque while the other provides negative. Let's make sense of that logically. If I were to push down over here, it's the same thing as pushing up over here. You see what I'm saying? Physically? If I had a rod in the middle that was pinned right here, and I push down on this side, it's as if I'm pushing up on this side. So these two things should have the same sign, and they do. They're both negative torques, causing clockwise rotation. This, though, responds to that with a counter or anti-clockwise rotation. So now we just have to use our signs and associate them. So what I'm going to do is I'm going to call this, I'll call this torque 1, torque 2, and torque 3 in that order from left to right. So the first torque is negative. So I've got negative 15. How far away is the 15 Newton force from the rotating point? How far is the 15 Newton force from the rotating pin or point? M, what do you got? 10 meters. Okay, please don't use 4 meters. That's the common mistake here would be to find the number that's next to that force and use it. But here's where it rotates. Here's where the force is applied. That's 10 meters. The angle is 60, but I need the angle on the other side, which is 120. Okay, remembering to use that angle right there of 120 degrees. Because, again, and I know it's the same, we talked about that already, R is here to here, and then the force is this. So what's the angle between those two vectors is 120. The second torque from 25 newtons, that's a positive torque. The force is 25 newtons. I kind of dropped units for now, so I'm going to keep doing that. At a distance of 6 meters from the rotating axis. Am I going to put anything else for that one? No, because it's sine of 90, and sine of 90 is 1. So I don't have to put anything else for the second torque. For the third torque over here, it's going to be negative. We know the value of the force. We don't know the lever arm. We don't know R, but we know the angle is 135. Okay, I'm going to use this angle over here, which is 135 degrees. Again, how am I getting these angles? They're supplementary. They add up to 180.
Is there a reason to put the negative sign on the outside of parentheses?
No, I'm just putting it in front of the symbol. Look at the last one I'm about to do also. All I'm doing is putting it there to show that I'm subtracting that entire quantity. Okay, that's what it becomes when I look at this. So where is the only variable you don't know? Right here. That's the only thing you have to solve for. Okay? The R value. Yes, what else?
Even if you were to put sine of 90,
You could.
would you?
Yep, that's fine. You're totally correct. Because sine of 90 happens to be 1, and 1 times this number will still be this number. So to be safe, you could always use the angle. Absolutely. Okay? Then we just solve here, right? It's just a lot of math we have to carry through. That's all it is. Okay, sine of 60 is going to be like 0.866, so 120 times 10 is 8.66 times this. It's going to be messy numbers. This will be 150. This will be 0.7071. Again, you'll memorize these, trust me, because it's root 2 over 2. You'll learn that soon. You're going to solve for r, though. So my suggestion would be sum these two values together first. All right, get a number for the sum of these because they're all numbers. And then I would take this whole expression right here and probably add it over to the right side. Okay? So can somebody give me a sum of these two values from here to here? Give me that value. The negative of this plus 150. What is it? 20.1? Okay. So Steve claims that this is 20.1. Agreed? Nice. Your claim is right, Steve. Now, we take this whole quantity, take a look, make math easier for you, all one step. Since this is a negative, add this entire thing over as if it were a number to the right-hand side. Okay, so the 20.1 is now going to equal, and when I do 10 times sine of 135, I'm going to get 7.07, and that's going to be an R value there. Is that correct? 7.07, and then dividing through. Yep. Okay, so again, 10 times sine 135 is 7.07. That's really 7.07 times R. I'm going to take that negative quantity of 7.07 R, add it over here to make it a positive 7.07 R, and then divide by 7.07. Okay? Now, one thing I do want to point out, this is a great question that somebody in the class asked. Can you get a negative R was the question? And actually, right off the bat, I said no. And I said, actually, yes, you can. In all of these problems, though, when we plug in numbers, we're never going to use a negative number. Like, for example, 6 is a distance. 4 is a distance. 6 plus 4 is a distance of 10. I'm not considering this to be negative because I'm going left. Okay? But if I somehow got a negative answer, it would have meant that the original placement, meaning on the right side, was incorrect. Where should it be placed? On the left side. That's all it would mean. Again, you're never going to use a negative number when you plug in the numbers themselves, such as 10 and 6 for distances. But if you solve a problem for R and you get a negative answer, it means that it's not possible if the force were on this side to be in equilibrium. The force is totally wrong and it needs to be on this side of the pivot point. That's all negative R would actually mean. Okay? Just a theoretical question someone asked. I thought it was good to answer. So this is in a state of equilibrium when that 10 Newton force is placed 2.84 meters away from the rotating axis to the right. The follow-up to this question is me just being annoying and going back to old chapters. Remember the chapter on forces, chapter 5? Okay, so the follow-up question is just to revisit stuff so that we don't forget things. I don't want you to start forgetting what we're doing with vectors and stuff. So it says at the end, is the rod also in a state of force equilibrium? Force equilibrium. And not rotational, but force. Force equilibrium is this, right? Not praying or anything, but literally just pushing against two things with the exact same force. So the question becomes, are these forces balanced? Are they balanced? Well, the problem we're going to have is that they're not acting in only the x or the y direction, so what do we have to do to them? If they're acting at an angle, what should I do to the forces? Into their components. Good word, Steve. He said break them up. Break them into their components. Take a look at this force right here. Which way is, forget rotation now. Forget rotation, which we've been studying for the last couple of days. Now think forces. Which way is this force pushing? It's pushing up and to the right, right? Up and to the right. This one is pushing down and to the left. And this one is only pushing down. So two of the forces are acting in the x and y direction, right? While the 25 Newton force is only acting in the y direction itself. But the other two forces are acting in both x and y. Okay, yes? We can, absolutely. We can absolutely draw a free body diagram of the whole rod as a single point in space. And that's how we'll approach this. That's a good idea. I like that idea. So let's go ahead and do that. I'm going to zoom out a little so I can keep seeing it. Let's draw a free body diagram here. we've got this force here of 15 newtons. We've got this force here of 10 newtons. And we've got this force here of 25 newtons. And again, I know that the rod has a length and it has dimension to it, but we are assuming for the sake of forces alone that it is a point in space that can be focused or concentrated, like the center of mass of the object. When it comes to torque, though, for torque, distance matters. How far away you are from the rotation matters for torque. For force, it does not matter. If you take the engineering elective next year, we talk about structures and truss structures and bridges in that class. This is one of the big topics we talk about when it comes to those. Actually, the seniors are starting their bridge projects next week on Monday. And we have just got over this in that class, which we're really kind of covering right now. I added this part to the lecture because it talks about rotations and forces, which are what bridges are feeling. They're feeling rotational torques and forces on them. So what we need to do is we need to take a look at this diagram here and break it into its components. But I need some angles, right? I need some angles, and it's not easy to look at these angles. So let's go through them real quick. So if I go back and look at my diagram, it will help to look at the diagram for this. Take a look at the 15 Newton force in the diagram. I'm drawing that little dashed line right here. That's the angle I want. It's always the angle with respect to the x-axis. So you go to the beginning point of the vector and draw yourself an x-axis. That's the angle right there. Well, what's that angle right there that I'm pointing to? What's the actual measure of that angle? 60. Because of? You remember some geometry?
Is it interior?
Good. Alternate or opposite interior angles. This is a transversal right here. Take a look. There's your transversal. These are your parallel lines right here. So this must also be 60 degrees, right? So we have to recognize that there's going to be a lot of geometry involved in these types of problems. So you're going to have to use the angles. So 60 degrees turns out to be the same angle, so it works nicely. That's great. Okay, so let's put a little dashed line here. Put our angle in. Then I go to the 10 Newton force on the top right, and I go to where the force begins, and I draw myself an x-axis. Okay? And again, I want the angle to the nearest x-axis. We've always said nearest x-axis, which is this angle right here. Okay? If we can't see, let me zoom in so we can see it better. Okay? We are focused on this angle right here. And again, this line is parallel to this line. And this is your transversal cutting across. So this angle must be 45. So 45 degrees will be the angle that we're going to use here. Okay? It says 45 degrees, not 450. Now that we have our angles, we can treat forces identically to how we treated them in Chapter 5 with cosines and sines for x and y. What?
So why aren't we using
The 120 and the 135? Because remember, when you look at forces, you want to consider where the force begins. So that's the beginning of the arrow, okay? Where the force begins, creating an x-axis always, and then the nearest x-axis to this vector. This would be the further x-axis, which is 135. This is the nearest x-axis, which is 45. That make sense? Okay? It will be useful because you'll get negative signs instead of positives in places you do it the other way. Now, what I want you to recognize, though, is that in the x and y direction, these things are pushing with either positive or negative. So we have to figure that part out, right? So in the x direction and in the y direction, let's see what we've got. So let's start with, and let's use this diagram. Forget the diagram at the top at this point, it doesn't matter. We've got everything in the FPD. From the FPD, we can see that this force is pushing to the right and up. So those are both going to be to the right and up. These are both going to be what kind of signs? Both positives, right? Recognize that the force is to the right and up, so it's positive for both. And it's going to be 15 newtons times cos 60, or 15 newtons times sine 60. And this is identical to what we did with forces. This is the x component, 15 cos 60. This is the y component, 15 sine 60. How about the 25 Newton force? Where does that go? The 25 Newton. Alex, what do you think?
On in the y direction, and is negative.
Very good, Alex. Well done. Good. The 25 Newton force is only acting down. Down is negative in the y. It has nothing to do with the x direction. If I push down on this table, it's not feeling a left or right force at all because I'm only pushing down. So 25 is only negative in the y. Good? The last force, it pushes down and to the left. Follow the vector. It pushes down and to the left. So down means negative here. To the left means negative here. So we're going to have a negative in both x and y for this last force. The value of the force is 10 newtons times, again, for x, the cosine of the angle. And for y, 10 newtons times the sine of the angle. So 2 forces in the x combating one another. 3 forces in the y, all acting on this member, rod, whatever. Numbers, make sure you are in degree mode. If these numbers will not work if not. What do you got?
7 point. Components or
Totals at the ends. What do we got for totals at the ends? You can just use all in one line on your calculator. The whole y direction, do it all in one line. The whole x direction, all in one line. You don't have to enter after every single entry.
Can you get a negative one?
Sure you could, absolutely. What do you got, Clemence?
Negative 19.0.
I agree. Negative 19 point, what was it? 0.8. I agree, that sounds right. How about the x direction? What did we get in the x direction?
we got 0.43.
0.43, I agree with that also. So what does this mean? What does this mean? What does this mean? What does it mean? Is it in force equilibrium, Maria? Why not?
Because the force is not over the y direction. It's first of all negative and possibly close to the 1
Careful. You have the right track, but these don't have to match up. Equilibrium means what should these answers be again? 0. So because they're not 0, that's the only reason it's not in equilibrium. So there is a net force downward, right, from the negative y answer, and to the right from the positive x answer. Again, this rod, member, beam, whatever you want to call it, feels a force to the right and down as a result of these values.
So, I mean, what does that look like?
It means that this is feeling a little bit to the right and a lot down. So the net force is acting down at an angle like that. It means that this member might snap, is what it means. Let me give you an example. I had my sticks here yesterday I was using. Did I show you shear stress? Did I talk about that with you guys? Alright, so this is a great example, this guy. So I just do that. So see the pin in the middle, right here? That pin is this, okay? Now, imagine if I took another piece of wood, like a 2x4, and this was maybe a little bit thicker, right? This is really thin. I'm going to use this because it's easy for me to use. But let's say I took a 2x4, and this is my actual member right here, okay? This pin is here, and this is what you're seeing. So this can rotate left or right depending on the forces. Now, what's going to happen is this. If there's a net force acting on this pin, and this pin is drilled into the wall, and the member is pointing, so my hand is now the 2x4. My hand is the 2x4 clamped over the pin. The pin is in the wall, so it cannot move. So this is the wall, this is the 2x4. The 2x4 feels a natural, an overall force down and to the right. So to the right, not much, but down a lot. So what's going to happen if it feels a lot of force down? Right? This is called shear stress. We're actually studying this right now in materials and engineering. We were talking about that a week ago. Shear stress is when a member gets pulled perpendicular to its axis. Imagine something like this, that suddenly you pull in both directions. It's going to snap very easily. If I try to snap this, try to pull this apart this way. Let's go. Sleeves are rolled up. Let's see. Go. You can't bend it. You cannot bend it. You can only pull it apart. Only pull it. You cannot bend it. Don't try to snap it. Right? Am I right? And how crazy is that? So the tensile strength of this wood is extremely, extremely large. It has a lot of tensile strength. It doesn't have a lot of strength in what's called shear or torsion. Now, the other part that's interesting is that if you bend it, though, it has very little strength. Bend one of these, and it snaps very easy, like a wishbone. But try to pull it apart, it's not going to work. In the senior course, they do a project, and I recommend they use dowels for one of them. And every year, students are like, oh, I have dowels. They don't work. But if you use them in tension, like a rope, think about a rope hanging from a bridge or like the actual cables on a suspension bridge. They have a lot of strength in tension. But the minute you push them together, in compression, they fail. So certain things have high tension strength, and certain things have high compressive strength. And this idea here is what would physically happen as a result. Okay? A long explanation for something that simple, but I want you to understand the physical nature of what's happening. On your own, or the person next to you, spend like, I don't know, you really don't need about 2 minutes to do this whole problem. Okay? About 2 minutes. Read through it, discuss it, get an idea of what you should do for this.
Is there anything that has such a tensile strength? Is that what it was? What was the word?
Tensile strength.
Is there anything that has such a low tensile strength that you just pull it apart? I mean, like cotton, I guess.
Such a low.
Yeah, low.
Yeah, a slinky. Right? Anything with a K value actually has very low tensile strength. It's made to stretch, but it's elastic, you know?
Yeah.
A plastic bag has a decent amount of tensile strength, but once you exceed it, what happens? You get that permanent deformation, and it gets weaker. Yeah. A rubber band. A rubber band has a lot of elasticity, but the tensile strength is very low, which is allowed to stretch. Usually, you'll see ropes or metal is high in tension strength, so you'll see that, but concrete is high in compressive strength. Try to do what I just did. See how I like crushed it just now with the wood? Try to do it with concrete. It's impossible. Compressive strength is much larger. Concrete has almost no tensile strength. That's why you see concrete with a rebar. Ever see concrete with bars through it? If the bars give it tensile strength, the concrete gives it compressive strength.
That's just a super.
It's like souping them up. Exactly. It's like saying, you know what? We don't want this concrete to eventually like start to rock and maybe the tension is going to snap that causes cracks.
What is it?
Rebar, R-E-B-A-R, not rhubarb, but like rebar, like bars that just go through. It could be any metal material. It's usually steel or something, but usually it's got like a helical. Yes, it's threaded, so that the threads are more surface area for the concrete to adhere to. And yes, so it doesn't slip out. But what I'm saying, when the concrete solidifies around the threads, those threads create more surface area to grip, so it doesn't allow the rebar to get pulled out. This could be confusing for one reason alone. Once you figure it out, it'll only take you about 30 seconds to do the math. This is where that other formula we were talking, or that other thing we talked about, which was like this. Remember we called this the lever arm? We talked about that quickly the other day. Lever arm? What's the definition of a lever arm? You already remember that? In those notes, if you swipe a little bit. Let's say that one more time, nice and loud, Em. And while Em says it, look up, please. While she says it, please look up, and this will help you. Go ahead, Em.
The lever arm is the perpendicular distance from the axis of rotation to a line drawn along the direction of the force.
So this force, if I continue to draw the line along the direction, when does it make a perpendicular angle with this? It's when it's right here. So again, watch what I'm going to do. As Em said, draw a line in the direction or along the direction of the force. That's where the force of 8 newtons is. I keep extending it. And this right here becomes my lever arm. So that distance is only 0.5 meters. The side of the square was given as 1 meter at the top. So that's a distance of 0.5 meters. So what I can do to figure out the torque from the 8 Newton force is use 8 newtons here and replace this entire thing with 0.5. I don't know the angle. I don't need to know the angle. Okay, I can recognize that this angle here is 90 degrees. So I can just use sine of 90, which is 1, and then multiply by 0.5. Or somebody in the other class said this, which was very, very intuitive. they said, well, isn't this really just the R value here? And I said, sure, it could be the R value, but then this is the angle theta right there. And we don't know that angle theta. So if you're going to use this as the R value, this would be 0.5 squared plus 0.5 squared equals hypotenuse squared. Find the hypotenuse, then use trig to get the angles, then use the angle to go back. It's a lot more work to do it that way. So instead, we think about the definition of the lever arm. And here, we can just extend the forces. So the 4 Newton force, you're going to do the same thing. Take the 4 Newton force, extend it, and we'll see that it's going to meet up at a perpendicular angle also 0.5 meters from the rotating axis. So they're both going to be 0.5 for this value right here for both torques. It's the force that will differ. The force that will differ. So the 8 Newton force causes a rotation that's going to be this way. That's the 8 Newton force, right? It's going to cause a rotation like that. That rotation will be counterclockwise. So the 8 Newton force will be positive. The lever arm is 0.5. Again, I'm not using the angle theta because I'm not actually using this distance in red. I'm using the distance in yellow, which is the perpendicular distance from rotation to force extended. Rotation to force extended is 0.5. So that value takes on this entire expression. So when I use my formula, it's F times the lever arm, that's F times the entire lever arm. And then the 4 Newton force causes a rotation this way, which is clockwise. And we said that clockwise is a negative torque. It's a 4 Newton force. Again, a half a meter away. So it's just 4 minus 2, or simply 2 Newton meters. Okay. Positive as an answer is because the 8 Newton force is the stronger one, and it's going to cause it to move counterclockwise. And counterclockwise is positive. It is positive. Okay, we got one more for today. One more. Questions on that? Okay, not the easiest problem because of the concept of the lever arm there. Okay, keep that in mind. Yes? Tomorrow. Yeah, that's the other section. Yep, that's fine. So 2 wheels are fixed to each other, and they're free to rotate about a frictionless axis through their concentric center. Concentric with center, sharing the same center. As shown above, 4 forces are exerted tangentially. We're going to use that word again later today. Yeah, probably for a little while today. Tangentially to the wheels. And these forces cause the wheel to rotate. So these 2 wheels are fixed. So although they're 2 separate wheels, it's like, how many of you used a rolling pin before? Have you ever seen a rolling pin? Okay. So the main body of the rolling pin is pretty big, and then usually it tapers down to like a handle at the end, and a handle at the other end. So imagine the main body being pretty wide, and having a large radius, and then the handle that it tapers down to of a small radius, that's like this. Okay? So this is a larger radius with another part coming out, extending from the board. So just to visualize so you can see this. Okay? That's what we're looking at. The larger radius has some forces acting on it, and then the smaller radius has other forces acting on it. And the question is, which way will it end up rotating? Okay, which way will it end up rotating? So looking at the diagram, it's a little confusing at first. You're not given any numbers. No numbers are given at all. So this is really conceptual, but you can use math to help. You know that the inner radius is double the or is half of the outer radius. One of these is r, that's the radius length. The other is 2r, that's the radius length. This is the force acting at 4 different locations. This one is double the force. So for each of these, consider whether they cause a positive or negative torque. We know that we have 4 of them here. We have to consider if they're going to cause it to rotate one way or the other. Could somebody give me a general consensus of what they think is going to happen before we get to math? Again, it says, do they rotate, right? Do they cause it to rotate? So we don't even need the answer. The answer is yes or no. This would be like constant multiple choice. Yes, no, not enough information, or, I don't know. No, is there a 4 choice for this? Yes, no, or not enough information. What do you think? Take a stab at it. Don't even do the math. Just look at the diagram. Just visualize this. Look at it. Think about what it's going to do. It's fine. We have examine and we have the second period. Think about what it will physically do. Is it going to rotate clockwise or counterclockwise? What do you think?
It's gonna rotate.
Mm-hmm.
Counterclockwise.
That's clockwise. We just did.
Yeah.
Yes. It's going to rotate clockwise. Take a look. Ready? Look. 1, 2, 3. Look at these three forces here. They're all going to cause rotation this way, this way, this way, except for this one, which causes rotation this way. And if you notice, this is a force F at a distance out of 2r. This is a force F at a distance out of 2r. So these are actually identical and equal and opposite of each other. So they're actually just going to cancel one another out. So these two torques cancel, which leaves you with two torques both acting clockwise. So as Alex said, the answer will definitely be yes, and it will rotate clockwise. If you're not really sure and don't see that, let me put some math up so you can see it. So let's start with, I'll use colors here. We'll start with this one in blue. So this is going to be a force of F at a distance of 2r from the center. And that's going to cause counterclockwise rotation, which is positive torque. Again, how do I know it's 2r? From here to here. Here to here. It's a distance of, not r, but 2r. And a force of F. Causing counterclockwise, and it's positive. In red next. In red. Torque 2. It's a distance out, 2r. It's a force of F, but it's causing clockwise rotation. Clockwise is negative. Again, a force of F at a distance of 2r. So you can see already that the ones I just circled, look at them mathematically, aren't they identical? So the answer is going to be 0 for these two torques. So pretty much all that matters is torques 3 and 4. So to figure out torques 3 and 4, let's use colors again, green. This one is again a force of F causing clockwise rotation, a distance 2r out. And last but not least, this inner force here, that one is the only one with double the force, but the distance out is only r. So that's what my overall equation ends up looking like, which needs to be just simplified. 2rf minus 2rf minus 2rf minus 2rf, or fr, doesn't matter, right? But each of these has a coefficient of 2. So this is 2 minus 2, which is 0. 0 minus 2 is negative 2. Negative 2 minus 2 is negative 4. So the answer becomes negative 4rf, or fr. Doesn't matter which way you put it. Because the answer is negative, as Alex said, it will rotate clockwise. Clockwise means negative, so this is going to end up rotating this way. And write yourself a note again, please, that the blue and the red torques cancel each other out. So if you could have seen that, this is a multiple choice, imagine. By the way, this one, so I started pulling some diagrams, which is a new question. I don't know if I can include this last year, maybe the year before. This one is one of the questions where it's like, from a multiple choice AP exam, where they assume that you're not going to do math, because to do math would probably take you a little more time. So the idea is that you really solve this conceptually by figuring out that these things are equal and opposite each other in torques. So as a result, these two things are going to be imbalanced. So will it move? Yeah, it's going to move. There's imbalance of torque. Okay, if there's an imbalance. You want water first or do the exam first? Alright, exam. Relax. Put your hands down. So you want to get an exam? I was in the middle of a problem with